let me start by quoting an example we have already seen. There is no metric on R2, or actually R2 minus 0, invariant under the SL2R action. Sorry?
Continuous.
Continuous. Maybe I will, in the future, forget this adjective when I talk about metric on a given topological space, kind of regarding a compatible metric. And okay, we proved that one. Yeah. Or if you want, the only semi-metric on this thing is a trivial one. So let me regard another SL2R space. Oh, but by the way, I should say there is essentially unique invariant metric on SL2R modulo SL2. I didn't discuss this, but I guess most of us are familiar with that. This is the hyperbolic method. So this space is called the works plane, and it is isomorphic to, it's naturally equivalent to this H2 that I was discussing last time. And let's, so the remark, I should say, SO2 is compact, while U is not. So there is a difference here between these two cases. This is U and U, right? So you can guess the dichotomy. Let me give one more example of this sort, just to convince ourselves more of this phenomena, and also to see a very useful technique that comes about. Consider A. This is the diagonal group in SL2, which I guess probably will abbreviate to G. There is no continuous invariant non-trivial symmetric on G model, which we don't. Looks like that, right? Just a remark, what I do here is a copy of the orbit G model. When I think of G, SL2R, this is just a remark. It has nothing to do with the material ours today, but this is isomorphic essentially to SO21, a group of acting on the free space, preserving 2, 1 form, the form, a Lorentz method. And the free space then as the light cone, hyperbolas of this kind of form, which are copy of this hyperbolic plane over here. I hope you're familiar with this. Also, some guys at least formed in the past, not only in the future. And these hyperboloids, which are, you may think of this space, the space G mod A, as the space of geodesics in the hyperbolic plane, or oriented geodesics, or pair of points at the boundary. Just a note. I mean, I will not use this stuff. And I claim that I cannot put an invariant metric on this piece. And how do we see this? In this space, G mod A, we have this and a fixed point of deposit A. Fixed point, just let me give it a name, X. I claim X if G acts on a metric space and X is a fixed point, is an A fixed point, then X is G fixed. There is a name to that claim. This is called the Mountner, this is the name of the guy, phenomenon. Mountner phenomenon. That's this technique that I'm about to illustrate. No, it's called Mountner phenomenon. Prove that claim. So we'll show that this X is also U fixed.
No, but this claim, G, you mean this SL2 of R?
Yeah, oh yeah, yes. This is in the context of our discussion. I'm sorry, this is SL2, and this is lambda inverse. I'm being very specific here.
Oh.
There are generalizations of this, which I am about to explore today. So far, I'm in the context of this example that I'm discussing now. I'm proving non-existence of metrics here. And this is because there is some A fixed point here, and this point, if there was a metric here, should have been G fixed. Okay? So what's behind this phenomena is the contraction action. Consider the conjugation action of A on U. So A normalized U. Right? And I can try to understand what happens if I'm taking lambda inverse and 1x01. I'm solving now very easy exercise, and now I'm taking the inverse of this guy, lambda inverse lambda, and I'm doing the multiplication, and I'm getting another element of that group U, which is and the thing is that if lambda tends to 0, then this guy goes to the identity matrix. This is the phenomenon that whenever you have a unipotent element, you can, by the action of the diagonal group, contract it to the identity element. observed. Now, consider this. We show now that for u in u, x a fixed ux is x by computing the distance between ux and x. Okay, I just need to give you a computation here. Okay, does that make sense? So, take, now since x is a fixed, I can apply here any element. I will take sequencing. Any an that I can think of, I will pick it in a minute. It will be these guys. In A is the same. A and x is x. Now I'm using the fact that the metric is invariant. So I can apply A n inverse. And picking A n right, well, that's not picking A n right, and this A n should be, no, actually it should be lambda inverse lambda, when lambda is some sequence tending to 0. This converges to dxx, to d, or if you wish, to d the identity times x comma x, which is 0. Right. But the right hand side is constant. It has nothing to do with this sequence I picked. So this is 0, it was 0 all the time. And ux is x. Yeah, this is little.
Well, I mean, this is a strange argument because on the left-hand side we have a constant sequence, and you consider its convergence and tending to infinite.
Yeah, I mean, it is a beautiful argument. It's not very standard, but it works. I mean, you can't deny its truthless.
Objecting this argument, I'm just saying.
It is strange. I mean, if you see it for the first time, it is strange. But it is correct and it is powerful. And I'm about to use it today in more and more sophisticated way. And, okay, but what did you get? We get that this point x is actually u fixed. And now I can either finish the argument by arguing just the same for the opposite unipotent group in a similar way, or adhering to the already known fact that there are on G mod U there are no invariant semi-metric, and this, so we can't have a U fixed point in a metric space without having a G fixed point. Maybe I'll give it as an exercise for you. It will follow in any case from the general theory I'm about to explore. But exercise, finish the argument. I mean, the argument, we did prove the claim, but finish the argument to prove that, sorry, prove that claim. Finish the argument with that. And let's start. Oh, well, is that fine? Okay, what's behind this? Maybe let me give theorem. While presenting a theorem, we'll use the notion of a proper action, which I will define in a minute. So let assume S and L R is acting continuously and isometrically on a metric space. X comma D, and assume further that there are no fixed points without fixed point. This is not really a loss of generality, because whenever you have an action on a metric space, I can just throw away the fixed point and take the remainder of the metric space and consider that action. So this, what I'm about to write down, will tell me about the structure of every action, every semantic action of this group SLNR. Then the action is proper, which is a very strong condition I'm about to explain. Okay. Next thing, yes, I'm about to explain. Let's start by defining what the proper map is. A continuous map between topological spaces X to Y is called proper if the pre-image of a compact space set in Y is compact in X. If for every compact K in Y, the inverse K is compact in X. It's just a reminder. The pre-image of a closed set is always compact. The image of a compact set is always compact. I'm assuming my space and how stuff is out even in the frame. The pre-image of a compact set need not be a priori compact. If you take the real line and map it into a point, the pre-image of the point is not compact. If you take the R2 and the projection on R, on the x-axis, the pre-image of a compact set will not be compact. If you take not R2, but only a strip in R2, infinite strip R times 0, 1, and project, this is proper. Proper saying that sort of the fibers are compact. It's a bit more than that, but let's do maybe a first order approximation of this statement. Whenever we have a property of a map, we can define the property of a group action. G act on X is proper. This is in the context of continuous actions on topological spaces. If the action map G times X to X times X, so this is Gx goes to X, comma GX is proper, is a proper map. Replace proper by any other property, and you define that property of an action.
Specification is not, I mean, the only possible one, because when you take this definition of a proper map, usually by an action we mean the function from g times x into x, and on, not the Cartesian square of x.
So this is the natural action map to look at.
I mean, the natural application of the general definition of a proper map here would be to consider the function from g cross x to x.
Okay, this will never be proper unless G is compact. The one. Okay, this is the definition, and somehow, whenever, if you, it's the rule of thumb that if you want to define the property of an action, use that property of when the property is a property of maps. You will apply to this. This is kind of the good point of view. Okay, you can. That's fine that you're not happy, but this is the definition.
This is a matter of definitions, but still this is a mismatch of incompatibility, because, well, an action in a particular...
Oh, let me try to convince that this definition is nice by giving a list of equivalent. So here is the exercise. The following are equivalent. For G atom X continuous action. The action is proper according to that definition that we gave. True. For every compact K in X, the set in G of G is such that G does not take K away of itself.
What is K inverse?
Is compact in G. Really? For every let me assume that X is retrievable here. In order to, I want to write down sequences instead of nets. I mean, you can generalize what I'm about to. 1 and 2 are equivalent. You can generalize what I'm about to write in 3 using the language of nets. I don't want to do this. For every sequence, Xn, converging sequence in X, and also, just a minute. So, also I'm assuming that, and Gn goes to infinity. We have Gn Xn goes to infinity. And I didn't say that my spaces are locally compact. So goes to infinity means don't have converging subsequence.
So it's not true, I forgot.
So could you be
Sorry?
it means that something tends to infinity?
So this is a short for doesn't have converging subsequence.
But are those spaces assumed to be locally compact?
So I did not assume that our spaces are locally compact. Yeah.
You might imagine, for instance, you have a space X has a discrete subset, and then those Gnxn form a discrete subspace of X. Then, in your definition, it means that they tend to infinity.
Excuse me.
Well, if you say that tending convergence to infinity means just not having
Any discrete sequence?
Then, for instance, if Gnxn formed a discrete subset of X, then they would tend to infinity.
Yes. Yes. So if you take, I don't know, the Hilbert ball and take the standard vectors with respect to the metric topology, I would say this goes to infinity in this context. This is just simple amusing. It's a short annotation for. So I'm asking you guys to show this equivalence. Now, what I'm about to do now before going and proving this theorem is take this Martner phenomenon that we've discussed over there and regard it in a more scientific way, if you wish. So, for G, LCSC is locally compact. Second countable and given sequence AN in G, so I assume my group is nice in second countable just for me to be able to discuss sequences. It doesn't really matter. And I'm assuming having this sequence in G, which is fixed implicitly in the definitions to come, define U plus, this will be a group in G. It will be all the U's in G, such that AN contracts in the form we discussed. Similarly, I will define U minus for the inverse sequence. These are the contracting groups.
What second countable means?
It is. It has a countable basis.
Okay.
It's
First countable is enough, actually.
sorry.
First countable is enough, actually. No?
Yes. Yes, but I just. For me, this is the standard setting. In ergodic theory, you want your spaces to be separable most of the time. And you want sequences to you want topology to be defined by sequences, etc., etc., etc. One can generalize. I'm not trying here to be as general as I can. This is not my wish. Or maybe let me introduce one more guy. These are all the U's which do not go either to infinity nor to identity by these sequences, both AN inverse and this guy are bounded or very compact. Sets. Exercise. You show that all these guys are groups. They are closed. These conditions are closed under taking multiplication and indices. Not necessarily closed, by the way. These are not closed conditions. Those groups are not necessarily closed. Actually, they are closed in the linear world. As we've seen, the unipotent group is an example of this, of such a phenomenon. And this is something which is typical to linearity. So this is a phenomenon that people see style. And actually U0 normalizes both. So if you take an element of U plus and conjugate it by an element of U0, it will still go to infinity because the element of U0 doesn't, so it will still go under conjugation by n to 1 because the element of U0 doesn't go to infinity to make things bad. Both U plus and U plus. So you get, in particular, that the group generated by U plus and U minus is normal inside the group generated by O. So why do I define these notions? Because, well, as we've seen studying mountain phenomena, it seems related to our problem, but also those groups are interesting for SLN. Example. Take G to be SLNR, A to be the diagonal group, AN, not just any sequence in G, but a sequence in A. This is very important here. Then up to passing to a subsequence. So every sequence has a subsequence such that the group generated by these. So I needed the sequence I needed to define this. These groups are dependent on the choice of AN, and maybe I need to pass a subsequence in order to make this group slightly bigger. Upon doing so, you will get all G.
But this group did not depend on the ordering of A and did they?
Not on the order. Yes, but I mean, if you take a sequence, I don't know, take AN to be a sequence as before, lambda, lambda, but every other element take the identity. You don't get a nice sort of convergence, right? Don't do that. I'm allowing you to pass to subsequence and take only the right elements.
What I meant was it's more like a subset than a subsequence because you need a sequence structure.
Oh.
So by passing a subsequence, you need to stay within one channel.
Actually, to go if you speak the language of Lie theory, then when you go on the Wald chamber, you go along one precise phase of the Wald chamber, or you're always regular, or you're singular in a given fashion. Don't move between two different singularities. If the Wald chamber looks like that, don't jump between these two pieces. Don't go back here every other step, right? I mean, just don't do stupid things.
I was confused in this example after this discussion, sideways discussion. I mean, do you mean that by after passing to a subsequence, do you mean that there is a subsequence of the sequence AN for which you have wanted?
Sorry?
Instead of up to passing to A, isn't it enough to say there is a subsequence?
Yes. There is a subsequence such that. Yes, this is what I informally meant. Thank you. Okay, so this is a claim. It is an easy claim. Let's observe this. Let's open this parenthesis. For every Eij, say, Eij, I mean, such a matrix, elementary matrix. Eij, think about what happens to this Eij when you conjugate it up by a sequence of A's. I will just multiply this one by various numbers. And this either will go to infinity or minus infinity are the same for me here, or to 0, or will stay within a bounded range, up to passing to a subsequence. And this is for every ij. Go to a subsequence that will have the same behavior for every ij, and you're done. Eij is in the union. U minus union, 0, union. This is the explanation of that claim. Is it clear? I'm brief in writing, but I want...
What does it say? A union.
Union. I mean, for every ij, Eij must have some specific behavior when I'm conjugating it with diagonal elements. Either this one will be multiplied by some, I don't know, lambda square or lambda mu inverse or something. These have to be precise. This I will be multiplied by lambda I, lambda j. This one. And up to subsequence, I will lambda I n, lambda j n. And then I go with n to infinity and something will happen.
So this is for a fixed sequence, AI?
For every given sequence,
For every given sequence, this holds. We can find a subsequence.
You should say for every sequence tending to infinity.
for every sequence, for every sequence, even if you tend to infinity, it might not hold. You need, it might not hold. You need to pass to a subsequence. Every sequence has.
Okay.
Please check this if this is not clear from this explanation. I don't want to spend more time on that. Okay. And and in fact, maybe I want to make one more remark here. Maybe I write here. If continuing this example. If an is bounded, this is uninteresting, then G will be one of these groups. Which one? Will be U0 itself, right? I mean, there is no dynamics. Otherwise, so if if AN is bounded, all EIJ will be in U0, as you see. Otherwise, for one, at least, EIJ, it will go to infinity or to 0. Otherwise, either U plus or U minus are non-compact. And so the group generated by this, U plus and U minus, is a non-compact group. Non-compact, but by a previous exercise that we had, is a non-compact. Well, by the way, when I say group generated for a topological group, it's the closed group generated by.
So, does this refer also to the statement of the example? So
Yes, the closure of, excuse me for that. In fact, for that specific example, I didn't need that. But in general, this is what I mean. Is non-compact and normal in that thing, which is everything, but the SLNR is essentially simple. Okay.
To say either because we don't need to say both.
Because I don't need to say both. Yes. In fact, it is both. Right? Think about EIJ. If it goes to infinity, think about what happens to EJI. So this is a phenomenon that happens in SLNR. A similar phenomenon happens for every semi-simple group. What is happening, what we are looking at here is what people are called the root groups. And this is the kind of behavior that we have with respect to elements in a Cartan group. Okay, so I will do today everything for our familiar guy, SLNR, but if you are familiar with Lie theory, or if you ever familiarize yourself, it will be very easy to translate the arguments to the general case. Okay? So I think we better take a break now, and we'll start with the actual mathematics, with the proof of the theorem, after the break.